method
So
we'll use to
irrationality
break
measure
it.
was not counted. Irrationality measure was not counted for the.
No, we don't know it yet.
Oh, you don't know.
No,
Yeah.
no, we know.
You just
We
said
know.
no.
We know
Well, we
only
know
zeta
it's
three.
no, we know zeta 3 is irrational, but we don't know its irrationality measure. So all we know is that it's at least 2. The techniques I've shown are all from 1850 or 1800s, which I've said, but Roth's theorem is actually a much more recent development. It's actually popped up in 1960. This was used to prove,
Like 75 years ago, 65 years ago.
well, it was used to prove that zeta 3 was irrational all the way in 1979.
So in the beginning, you have some other concept.
In
But why? Which concept?
Well, actually, we did show that if a number has infinite irrationality measure, it's transcendental, but that does not imply the converse. Some transcendental numbers, including pi, have finite irrationality.
How about you relate with this approximation we have to Riemann zeta?
The Riemann zeta function in integers is not known to be irrational. So zeta of 2, it's known to be irrational. That's the famous spatial problem. Zeta 4, zeta 6, at all even integers, it's known to be irrational.
How will you take the n as integer when you are expecting some function?
Oh, sorry? Oh, yes.
Functions you are taking as a polynomial or
Yes. So the assumption at the beginning, what we wanted to prove was that if alpha is algebraic, it has a finite irrationality measure. Theory is often viewed standalone, but two other popular areas of study are looking at it from an analytic angle and an algebraic angle. Today, I wanted to show you where those two angles exactly intersect at a very nice part of number theory called Diophantine approximation. So let's see, pen mode, okay. Can I just write here, and where's the eraser? Can I just erase it? No, that's the highlighter. So, oh, okay, that's nice. So, let's start with the quintessential irrational number. What is Diophantine approximation? It's just approximating an irrational number with rational numbers. So we can start with pi. Pi is about 1415926535897. That's about all of the digits I can remember, and it's also about adequate for every single physical application in history. So then, why do we need more digits? Well, because pi's mathematical properties are some of the most interesting to study. So let's first take the naive approach to approximating it. What happens if we just approximate it by taking the first n digits and truncating the rest? Well, let's take approximation 1 to just be 3, and of course that's a rational number. You can take approximation 2 to be 3.1, which is also a rational number. All of these approximations will be rational numbers by virtue of them terminating. We're terminating this approximation after finite digits. So 3.141, and so on and so forth. So this is the very classic way of approximating an irrational number. Now, is it good? Well, then the next question becomes, how do you define a good approximation? Now, that's a very good question. You could say, well, the discrepancy between the number we're trying to approximate and our approximations approaches 0 if the approximation number approaches infinity, but that's true of every approximation, even the slowest ones. So that's probably obvious to you already. Maybe we can measure it by taking the discrepancy between the approximations and the actual number and measuring it with respect to the approximation number, but that's also a terrible measurement. Why? Well, let's say I have approximation method A, which I'm going to describe with A1 is 3, A2 is 3.1, A3 is 3.14, or it could be anything. Now, I could just describe another method of approximating B such that the nth entry of B is just the 2nth entry of A. Suddenly, B is twice as good as A, and yet there's no more efficiency in the approximation. Both of them are very bad approximations, which means this is also a bad way of measuring how good an approximation is. Of course, the only way left is measuring the discrepancy in the approximations versus the denominator of the approximations. How does that make sense? What's the intuition behind it? Well, I like to think of it this way. If you have some irrational number on the board, essentially, when you're trying to approximate it with a rational number of some denominator n, you're holding it up to a ruler where the gap between each mark is 1 over n. So, of course, if n is large, you're going to be left with a very inaccurate ruler, very few marks to choose from. And, of course, the mark you do choose is going to be very far off in terms of accuracy. But, of course, increase the denominator, increase the number of marks on the ruler, well, it's technically infinite, but increase the density of the marks, and it's guaranteed that you'll find a closer approximation at some point. Now, of course, that doesn't mean you always get a better approximation when moving to a higher denominator. That's not true. But if the denominator is 100, which is going to be a worse approximation than if the denominator was 1,000, and so on and so forth. So, even though we don't know in specific that increasing the denominator will always make the approximation more accurate, we know in general that it's going to follow that trend. So now, let's see if we can measure the speed of our approximation that we used for pi earlier. A1 is equal to 3, A2 is equal to 3.1, A3 is equal to 3.14, etc. Now, of course, let's write d, where dn is just the magnitude of the number we're approximating, in this case pi, minus the approximation, the nth approximation. So what we get is the first discrepancy is 0.14159, the second is 0.04159, and so on. It's pretty obvious that dn is going to be on the order of 10 to the minus n. So, for example, this is on the order of 10 to the minus 1, this is on the order of 10 to the minus 2, and so on and so forth. In fact, you can actually say it's bounded between 10 to the... You can actually say it's bounded between 10 to the minus n and 10 to the minus n plus 1. Oh no, that's not an equal sign. So, what this tells us is that since dn is very roughly proportional to 10 to the minus n, and the denominators of our approximation are proportional to 10 to the n, not just proportional, they're exactly 10 to the n. For example, a1 was 3 over 1, oh wait, it's actually 10 to the n minus 1. A2 was 31 over 10, A3 was 314 over 100, and so on and so forth. And so, these approximations right here, the denominator, so if we write an is pn over qn, qn is just going to be 10 to the n minus 1. So what that's telling us is that the discrepancy is essentially proportional, well, not proportional, but it's approximately equal to 1 over 10 times q to the n. So this is our approximation accuracy for right now. If you really wanted to, you could write this as pi minus pn over qn is less than 1 over 10 qn. So That's nice, but can we get a better approximation? As it turns out, yes, this is actually a terrible method of approximation. Here's what we're going to do. I am going to write out a fraction with denominator 1, 2, 3, 4, and so on. And then the numerator is going to be filled with the integer that provides the closest approximation to pi. So now when we start, well, the closest approximation to pi with denominator 1 is obviously 3. You're just looking for the nearest integer. For 2, you have two choices. 2.5, 3, well, you have three choices. But of course, 3.5 is obviously farther, and 2.5 is also farther. So we just have to choose 3. So this is going to become 6 over 2. Same story for 3, but 4 is our first actual improvement. If we go for 13 over 4, we get 3.25, which is considerably closer to the value we want than 3 is. Then 5 brings another improvement. 16 over 5, 3.2. We're getting even closer. Then 19 over 6, 3.16. We're getting an even closer improvement. And what you might see next is a very familiar face, 22 over 7. That's another improvement, 3.1428. But of course, once you stray away from that, you get 25 over 8, which is 3.125. That is worse. Then you get 28 over 9, 3.111. That is also worse. And then you get 31 over 10, the thing we just saw earlier, which is even worse than that. So what we're seeing is the streak after 22 over 7 of just failures and failures and failures. But that's probably because our sample size is 10, and 7 is pretty close to that upper band. Surely there's a lot of them after 7, and we're just not seeing it, right? So when is the next denominator that actually provides an improvement? What do you think? You want to take a guess? It can just be an order of magnitude. Oh. Well, it turns out the correct answer is not in the 10s, not in the 20s, not in the 30s, not even in the 40s. It's, of course, 57. In fact, 179 over 57. What's the reason for this gap of 50? But surely after that, we're going to get this continuous stream, right? Because 5 is an improvement over 4, 6 over 5, and 7 over 6. So surely we're also going to get an improvement of 58 over 57 and 59 over 58. But no. The next improvement after this is actually at 64. And then the next improvement after that is at 71. And then the next improvement after that is at 78. And then this continues all the way up until an extremely famous approximation up there with 22 over 7, 355 over 113. And then after 113, you could hazard a guess at what the next improvement would be. 355 over 113 is already a very good approximation, but surely we can find a better approximation to pi within the next 100 denominators or so, right? Unfortunately, no. The next improvement is at 19,102. So this unpredictability, where is it coming from? Where are these numbers originating from? And if you looked closer, you might notice something even stranger. Why isn't it? Come on, dude. Okay, there we go. You might notice something even stranger. Let's say we break this up into chunks, which are split by those abnormal jumps. So the first chunk is just 3 over 1. The second is 13 over 4, 16 over 5, 19 over 6, and 22 over 7. And the third chunk is 179 over 57 continued fractions. A continued fraction is just another way of writing a number, similar to, a power series or an ordinary decimal representation. all you need to do is write a0 plus 1 over a1 plus 1 over a2 plus 1 over a3 plus, and it depends on whether it's a rational or irrational number, but this is going to go all the way down, just like the terms. So how exactly would we represent pi, and what's so special about this format? Well, represent pi with this, first, this is going to be less than 1, which means a0 has to be the integer part, and the integer part of pi is just 3. Okay, then we isolate it to this. Now, we want to find what a1 is. So I'm going to call this x, because the integer part of this x right here is a1, and the rest is the rest of the continued fraction. The tail, some people say. So this is equal to pi, we just have to take the floor of x in order to know what's next. And in this case, since x ends up being 0.14159, well, 1 over 0.14159, it's going to be 7. And then next after that, 15. And then next after that, 1. And of course, next after that, 292. So the continued fraction we get is 3 plus 1 over 7 plus 1 over 15 plus 1 over 1 plus 1 over 292. So now we call a convergent to these continued fractions what happens when you just truncate it and cut off the tail at some point. 3 plus 1 over 7, well, that's 22 over 7. 3 plus 1 over 7 plus 1 over 15, well, that's actually 333 over 106, which comes right before 355 over 113 in the chain. But its older brother is much more well known because it provides a substantial improvement with pretty much no change in the denominator. Because the next convergent, the pi is so small, the next continued fraction numerator here is so small. So this is 355 over 113, but of course, because of random chance, this guy over here happens to be one of the largest numbers we know in pi's continued fraction expansion, 292, which of course means the approximation including it will be slightly better than 355 over 113, but it'll take so much more space in the denominator that it's pretty much useless. So now we know what's so special about these. But what's so special about the guys in between? What we like to call the semi-convergence? Well, some of these questions I'll leave up to you, though this one I'll answer right away by saying it's related to the Stern-Dracot tree. What happens is you just take this sequence right here. Don't ask about the 1 over 0. That's part of the notational abuse. And what you do here is every single one of these guys has 2 children. Don't take that out of context. 0, 1, and then this has a child with 1 over 1, what we call the mediant, which, unlike regular fraction addition, ventures to actually add both the numerator and the denominator, like you probably did in elementary school. And then you have 1 over 1 and the notational abuse thing over here, which gives you 2 over 1 on this side. And through this construction, by taking the medians over and over again, like a sort of Pascal triangle, you can converge to every single real number, including irrational numbers. And every single rational number can be listed by this procedure. The funny thing here is that the process of converging to an irrational number through the Stern-Dracot tree, which uses medians, happens to be the exact same as the process used to converge to irrational numbers by continued fractions. And so what you're seeing here, 13 over 4, 16 over 5, 19 over 6, 22 over 7, is the mediant of some multiple of the previous convergent and another multiple of the previous convergent, which happens to give you something completely new. So now pi's continued fraction is chaotic, which means studying it doesn't do us that much good. But what else are continued fractions really useful for? Well, let's go back to that measure from earlier of how good an approximation was. We wrote something like pi minus p over q, or pn over qn, is less than 1 over qn. Now, because of the way these approximations work, as I stated earlier, there are hiccups. Sometimes the accuracy happens to just go down even when you increase the denominator. So instead of saying this happens for all qn, or even that this happens for all qn after a certain n, all we can really say is that this happens for infinitely many n. Now, infinitely many n can mean pretty much anything. It could mean the squares. It could mean anything that's really, it could mean any sequence of infinite numbers. It could be as dense as you want, or it could be as light as you want. All that matters is that it happens infinitely many times. So this equality is satisfied for infinitely many rational approximations. So now, it turns out that there's a difference between rational and irrational numbers. One can be approximated with rational numbers more well than the other. And of course, common sense tells you that rational numbers can be approximated better than irrational numbers, right? But unfortunately, common sense is not worth much in mathematics because it turns out irrational numbers are actually more. What happens is you can expand it into something like a over b. And of course, by making a simple common denominator, you can just make this aq, why did I write a g? aq minus bp. Now, what you know here is that aq minus bp is only equal to 0 if a over b is equal to p over q. And this inequality is false infinitely many times. Of course, it's also true infinitely many times, but just like there are infinitely many multiples of 3, there are also infinitely many numbers that are not multiples of 3. Which means there are going to be infinitely many times where this is 1, or something greater than 1. Which means that you can say infinitely many times that this is satisfied. It's greater than or equal to 1 over bq. Looks like this. 1 over bq maybe looks like this. But of course, if you have even 1 over q to the 1.001, it's eventually going to start out greater, but undertake it, if you can call it that. It's eventually going to end up less 1 over bq. And of course, that makes sense because 1 over bq is always going to be greater than 1 over q to the 1 plus n for any positive at some point. What I do is just take this, and suddenly it's always going to be true when q is greater than the nth root of b. I mean, oh wait, do that for erasing. So that means with rational numbers, the best approximation power you can get, any rational number satisfies this inequality infinitely many times. But of course, if you change that to 1.001, that's a little bit more flimsy. So we call this power right here, the supremum of this power is what we call the irrationality measure. Now, I think that is a really bad name because there's not much irrationality to measure here. Something is irrational or it's not. It's an indicator function. So it's a misnomer, but what it really should say, I think, is approximation accuracy measure or something, but that rolls off the tongue worse. So the irrationality measure of a rational number is always 1. But what about an irrational number? Well, here's what we can do. Now, if I take an irrational number, let's call it alpha, that's not a very creative symbol, and multiply it by any number, k, it's always going to have an integer part and a decimal part. Now, what you'll notice is immediately this does not work for rational numbers, because if rational numbers can be expressed as a over b, then multiplying it by b totally removes the non-integer part. So this is going to be non-zero, and this is always just going to be an integer. So what we can have now is, if we have k alpha is equal to ik plus dk, here's how the standard proof goes. Let's say we take I1, I2, I3, all the way up to IN. And then you also have dk over here. You can take d1, d2, oh sorry, I should carry 0 here, d3, and so on, all the way up until dn. So now, what you'll notice is that there are n plus 1 entries here and n plus 1 entries here. Now, what I'm going to do is take the interval from 0 to 1, which is where all numbers dk lie, because, it's the decimal part. And I'm going to slice it into n evenly sized intervals. Well, actually, yeah, now that I think about it, I0 and D0 don't make sense to include, because they're going to be 0. So I can slice this, say, into n minus 1 intervals. Each of these is going to have length 1 over n minus 1. Now there are n minus 1 intervals, and can I erase this? Yeah. Now there are n minus 1 intervals and n numbers to fit within it, d1 to dn, which of course means that you will somehow find 2 of these numbers in one of these intervals. That's how the pigeonhole principle goes. You have n pigeons, or n decimal parts, n minus 1 boxes or intervals to fit them in, and so of course you're going to end up with 2 in one box. And so what that means is there exists some a and b from 0 to n, such that, well, the distance between dA and dB, sorry, that's a little bit scuffed, dA and dB is less than or equal to 1 over n minus 1 by virtue of what we just did here. And so what that means is, I think I have to make a little bit more space that's not too visible. What that means is, just expanding this, we can get, since IA plus DA is just going to be A times our irrational number, B minus B alpha. And then what we get from here is that IA minus IB minus, minus A minus B alpha, I really don't want to make a sign error here, is less than or equal to 1 over n minus 1. Since there's an absolute value here, I'm going to justify switching the signs. And now, all I'm going to do is divide both sides by A minus B. So you get alpha minus IA minus IB divided by A minus B. And that's going to be less than or equal to 1 over n minus 1 times A minus B. And as long as A and B are distinct, we are guaranteed that since A and B can range from 1 to n, there is no way A minus B is greater than n minus 1. Which means that this fraction, of course, will be less than or equal to 1 over A minus B squared. So what that tells us is, if we just replace the A minus B with the denominator symbol, and the IA minus IB with a numerator symbol, which is valid since remember these are integers, we get alpha minus Pn over Qn is less than or equal to 1 over Qn squared. Somehow, miraculously, we have shown irrational numbers can be approximated faster than rational numbers. Now, that's just a little bit perplexing. But now, here's the most important part. We've been looking at analytic number theory this whole time. But now we can also look at a little bit of algebraic number theory this way. This was how the first transcendental number was invented, in fact. Well, discovered, I guess you could say. So Joseph Liouville, in 1844, thought he could devise a number such that no matter what the integer you put in here was, this would always be less than or equal to it. So essentially, he thought he found a number that could be approximated so fast, it couldn't be described or it couldn't be bounded by one of these. And so what was his number? Well, 0.110001 0.000000000001 and so on and so forth. What is this pattern? Well, it's just the sum from n equals 1 to infinity of 10 to the minus n factorial. So the gap between each one is essentially n factorial minus n minus 1 factorial, which is a pretty huge number. So now, what's so special about this that causes it to outshrink, I guess, any inverse exponential? Well, we can't call it an inverse exponential, but anything of the form qn to the minus k. Well, here's the secret. If you take a rational approximation that's, for example, if we take 1 over 10 to the 1, which is approximation number 1, this is just 1 over 10 to the 1 factorial, then what's going to be left over is 0.010001, and so on and so forth. Which means it's going to be on the order of 10 to the minus 2. See, 10 to the minus 2 factorial. Then A2 is going to be 1 over 10 to the 2 factorial. And D2, the discrepancy is just going to be 10 to the minus 3 factorial. And of course, when you take 10 to the 3 factorial, the discrepancy is going to be 10 to the minus 4 factorial. And so, the nth discrepancy is equal to, well, the approximation itself is 1 over 10 to the 3 factorial, but Qn is just 10 to the n factorial, which means that since this is just 10 to the minus 3 factorial to the 4, what we're getting here is 1 over Qn to the n. So what we're getting is an exponent that changes with the level of accuracy. The exponent is going to grow. And of course, as the exponent grows, this function is going to shrink. 1 over Qn to the n is going to be less than 1 over Qn to any non-changing number at some point in time. As soon as n is greater than k, it's wraps. So Liouville found a number which couldn't be approximated by, well, whose approximation couldn't be bounded by any inverse polynomial like this. But of course, how does that prove transcendentality in any way? We haven't gone into the actual algebra yet. Well, here we go. Here's the standard proof of what we call Liouville's theorem, which states that if this approximation cannot be bounded, cannot have a lower bound that takes the form 1 over Qn to to the k for any integer k. So if cannot have lower bound for infinitely many k, or sorry, not infinitely many, for any integer k, then alpha is transcendental. Well, actually, what he did was he proved sort of the opposite, which implies this. He proved that if alpha is algebraic, there is no way it cannot be approximated this fast. So how did he do it? Well, he started by taking a function which had a zero, the number in question, alpha. And we want it to be a minimal polynomial, which we know will always exist. And so that will imply, if f is a minimal polynomial, that f prime of alpha is not equal to 0. And since it's a polynomial, that also in general implies that f is continuous. So what that does is allow us to take, let's say, this is alpha right over here. This is where our function f has its root. And so we are enabled this way to take some, I don't want to call it delta, let's call it epsilon, that's a little bit more standard. This sort of epsilon circle from alpha minus epsilon to alpha plus epsilon, where in this region, it's guaranteed that except for alpha, there will be no root. We know there is some epsilon that satisfies this, since f is a minimal polynomial. But now, since we also know this, let's draw, I need more space. This is f. Let's draw f prime. So if I just had to copy my drawing, I will say f prime looks like this, or something of that sort. And so it's negative at exactly that point in time. No, that's not where I want to put it. Minus sign on this doesn't matter much anymore. We can rearrange this and write alpha minus p over q is equal to f of p over q minus f prime of c. And now, what is f of p over q? Well, consider that since f can be written as some polynomial, let's say from I equals 1 to, let's say it has degree n, or I equals 0, that's what a polynomial looks like, of ai x to the I, then if we plug in p over q, we get ai p to the I q to the minus I. And so this can be written as the absolute value of whatever is there. Now what I'm going to do is multiply the numerator and denominator by q to the n. So you get q to the n minus I over here, and q to the n f prime of c here, since f has finite degree n. And since this sum only goes up to n, this is always going to be an integer. Q, since p over q is a rational number, q has to be an integer. This is an integer as well. This is always an integer since we defined f at the beginning to have integer coefficients, which means this is going to be a sum of integers. Which means it has to be greater than or equal to 1. And of course, we can set f prime of c, well, it's bounded between minus m and n. But we can just say it's equal to 1 over b q to the n for some b. That's just a fancier way of writing f prime of c. So now we've just shown that any algebraic number has approximations that will always be bound by the degree of the polynomial they're a root of. In fact, there's a more complicated theorem, which I can't prove today, called Roth's theorem, that tells us that every single algebraic number, in fact, has an irrationality measure of only 2. This is always going to be 2. But of course, Liouville didn't have the technology in his day to prove that. So, since every algebraic number will have that finite irrationality measure, something that can't have a finite irrationality measure must be transcendental. And that's how the first number was proved to be transcendental. So would you look at that? In just this 30-minute session, we've went from talking about Diophantine approximation to talking about continued fractions to talking about the Stern tree, and then finally talking about irrationality measure and Roth's theorem. So in just a few minutes, we've went through a lot of the introductory steps in analytic and algebraic number theory. Now, I think this is very inspiring that we've done all of this without even introducing really a second of calculus. Well, we used a little bit of calculus in the intermediate value theorem, the mean value theorem, and the extreme value theorem, but without introducing even any multivariable calculus or any really complicated algebra. So as you can see, with totally elementary methods, this is what you can achieve. Number theory is really just beautiful like that. In fact, elementary number theory is not just handicapped number theory. It's not just a challenge of proving things without complex techniques. There are so many things that can't be proved with complex techniques that can be proved this way. So I'm hoping that this session inspired you to really go into number theory a little bit more. Even though it has very basic beginnings, it gets complicated very fast. It also gets very interesting very fast, as I hope you saw in this session. So thank you everybody so much for having me. I hope you enjoyed this session as much as I have given it. And hopefully I'll see you again soon.
This is the one.
Thank you.